thank you for the introduction. So yes, as the title says, I'm here to talk a bit about Rust and what makes Rust special. So for me, the interesting question was, how good is idiomatic Rust? Because nowadays we have a lot of programming languages out there, and you can write fast code in many of them. But the question is, how fast is it going to be by default? And I think Rust is in a pretty good position for that. And so one of the things I often hear about Rust is that safety is somewhat of a concern for people because it might get in the way of performance. So that's something I've been analyzing, especially for my field of interest, which is HPC, scientific computing or machine learning. And to first introduce Unsafe to those people who might not be familiar with it yet. So it's not that Unsafe is completely changing the way in which we compile our Rust code. Unsafe is really just a really superficial check of whether you've marked your code region or your function as unsafe. And in that case, you get 5 superpowers from Rust, how we call them. So really interesting for scientific computing are mainly the first 2, which I've highlighted here. So Unsafe Rust allows you to dereference a raw pointer. So that's pretty much basic C style. We usually don't really use raw pointers. That's more a thing of like FFI, if you want to call it to other languages. But there might be some application for it, right? The second case which we have is call an unsafe function or method. There are some provided by the Rust standard library, but you might as well write your own unsafe functions, which you usually do if you cannot prove that all preconditions might be met. So you want to like outsource the responsibility to a user of your function. And there are 3 more cases. So you can access and modify a mutable static variable, which, I mean, globals are kind of bad. You should not do that unless you know what you're doing. So it's rarely the case that you need to do it. We also are able to implement an unsafe trait, which is a design. And finally, you can access fields of a union, which is similar to enums, except they are not tagged. So you are to some extent responsible of what you do with them. I don't really see much usage of unions in Rust, but they do exist. And just to point out again, once we checked whether you do one of those 5 things, and if you're in an unsafe block, that's all we really do with unsafe. And afterwards, we throw the information away. So from the Rust MIR onwards, the whole code can either be considered completely safe or unsafe, however you want to see it. It's not changing our compilation model. So as I said, one of the reasons why I wanted to give that talk and talk a little bit about Unsafe Rust is I feel like there's a misconception about it out there, and people often feel that Rust is kind of great, it's safe, but then it's slow. Or it's fast, but then you have to write it like C. So that's something I've been told by, I've been reading a lot online, but like even people here, some folks I've been talking to were concerned about it. So I want to give some examples of why it's not only in general wrong, but like it's more the opposite. So our safety gives us a lot of compiler information, and not all of that is used by LLVM yet. Nikita talked a bit about it yesterday, but we hope to make more and more use of all the information within LLVM and actually get performance out of it, and not just catch up to other fast languages. So about automatic differentiation, it's in general a pretty basic concept. We had it eventually in calculus in the past. So if you want to look at the function, here is x times x or x squared. The derivative of it is 2 times x. It's a pretty simple concept. You see like how much does the function change at a specific point. And I mean, such a basic example isn't interesting for computer science, right? So in reality, we do have functions which have various inputs, various outputs. A common one in machine learning, for example, are neural networks, which have huge tensor inputs, images, and weights, and a single output, which is our loss. So in that cases, it becomes much more interesting about why we want to differentiate something. And that's also the point where AD then comes in our performance benchmarks. So a while ago, there was a new autodiff tool out there. I mean, in the past, we were able to differentiate Python quite well. A few other tools existed, but then 2 PhD students came along and thought about what actually would be the case if we do it on LLVM level. And as it turns out, LLVM does not only give you a benefit of supporting various languages at once, it also allows you to get a quite decent speed up over pre-existing tools. Because what usually happens is with AD, you have some source code transformation. So you get some code in and some code out, and the new code which you get out on your source level still computes a derivative. That's kind of nice because then you can analyze the code. Like as a user, you can see what gets generated by your tool. But performance-wise, that's a bit tricky, because the reference pipeline, which is highlighted here in orange, does pretty much like source level AD. So an autodiff tool is first applied, then we optimize our code and see what the performance comes out. And the same tool now is applied in a different order, where you first take your input code. In that case, it was C++, but it doesn't really matter. You lower your input to LLVM. You first run optimizations, then you differentiate, and then you optimize again. So it's the same number of optimizations. It's just a different order. And apparently, you are a lot faster. It's a median speed of 4.2x, so it's pretty decent. And the issue we have in Rust, as again mentioned already yesterday, we don't really do many optimizations on Rust IR. The few which we do on MIR are mainly there to improve compile times, because we do before monomorphization to make life easier for LLVM. But that doesn't mean that our Rust IR is in any way efficient. So we do need to rely on it, and that's the reason why we are kind of interested in using LLVM-based autodiff in the Rust compiler. So one of the reasons, well, that was pretty much my selling pitch to the Rust compiler people. So backpropagation for neural networks is maybe the most glamorous at the time, but there are a lot of applications in high-performance computing and scientific computing out there which make use of automatic differentiation. So these are the ones I'm in touch with to some extent, but obviously there are much more. So about the current status, it got approved by the compiler team. It got a bit later approved by the language team. So now we have been able to upstream most of our Rust fork, including autodiff support. There's one open PR, as you can see, but we do hope to get it in a month or so. The work is also further supported by the Rust Foundation through a fellowship, so thanks to them for that. And yes, so now to get back to the interesting part of my talk, why am I claiming that unsafe code is slow? So I have 5 benchmarks. It's classic C++ versus Rust. The C++ is taken from previous papers, so it's actually quite well optimized. It uses all the fancy tricks, restrict, has been well profited and analyzed, so it's not just some random code. And I've been adding some more variations to it. So we have now our C++ code with restrict and without. And I mean, without is usually what people would write in your dependencies. And we have Rust code, which is written as a normal Rust code, high-level types, references, vectors, whatever you're used to in Rust. And I have a raw pointer version of Rust. So that's pretty much, if you treat your Rust code as it would be C, what do you get out of it? We, well, for nicety, have 2 competing C++ tools, Tapenade and Adapt. Tapenade supports Fortran and C++, which will be relevant later. And Adapt is for C, is like code. So to not talk much more, here are our benchmarks. And just to make it clear, all the code is handled by AD tools, but if you leave those AD tools out of the loop, everything is completely identically fast. It's in a 1 or 2% range of differences. So the only interesting part here is really AD. How much does the performance change if we want to compute derivatives? It's 5 different applications, and if you pay closer attention, so the first 2 are Rust, the second 2 are C++ using the same autodiff tool based on LLVM, and the green ones are completely unrelated autodiff tools which fall a bit behind. So the dark red and the light blue ones are the ones which are optimized. So the first one is Safe Rust, the light blue is C++ using all the restrict qualifiers wherever you can. And then we have in orange the Rust raw pointer, which is pretty much C-like code. And we also have the C++ version just by stripping our no-alias information from restrict. So to have a slightly closer look at how the performance is doing, FFT is one of those benchmarks where C++ were close, but not identical with Rust. So we have 0.54 seconds for both Rust versions and 0.64 for the C++ version. The second one I haven't been added because there was no alias usage, no restrict usage in that case anyway. So Rust is slightly ahead, and that's interesting. I mean, I've been talking about you should not write your Rust code like it would be C code, because we'll see later why. But there are some cases which are actually valid, and that's which I've highlighted at the beginning. So you can mark small code regions as unsafe and use one of those superpowers. And one of them is calling unsafe functions, which in this case are provided by Rust standard library. So instead of calling the standard swap function, which does some bounds checking, we now call the swap unchecked, which trusts you on having your indices inside of your vector and slice bounds. And that gives us approximately 40% performance improvement. So it's one of those cases where LLVM is not yet able to do successful bounds checking. We can help out with that, no issue. And hopefully at some point we'll be able to fix this specific case in LLVM. I've heard that C++ is also, to some extent, curious about using more bounds checking by default, so it should hopefully be some work done in the future. And to look at the next, and in my opinion, most interesting difference, that's a benchmark where we have three first spots. The first one is on the left side, Rust in a safe idiomatic style. The next one, just slightly behind, almost close to noise, is C++ using all the restrict qualifiers everywhere. And the third place is, in that case, Tapenade, which is a tool which also supports Fortran. So we see a 10x performance penalty for Rust if you start writing your Rust code as C code. And we see still a 4x performance penalty for C++ if you remove all your restrict qualifiers. And if you think about why, and if you look a bit closer about what AD does, that actually makes a lot of sense. So to explain a little bit what AD does on a technical level, we kind of go along those functions which you care about, which you want to compute gradients for, and we double their function length. The way we do it is we look at the code, we mirror it. So originally, you've been running your code once from the beginning to the end. Now, instead of leaving the function at the end, you'll run it in reverse order from the end to beginning, which means effectively double the length. And then we modify both parts of this new function. So in the forward pass, the original one, we cache variables, which we might need later for computing derivatives. And in the second pass, the new reverse pass, which we have added, we either reload stuff which we have cached before, or we recompute. Which of the two we do is kind of a tough question. There's no clear answer to it, but there are good trade-offs. And that's pretty much the reason why we do need unsafe in automatic differentiation, and therefore all applications, why we need restrict and no alias info in all of these applications. Because if you think about what you want to cache, it's everything that gets overwritten and that's needed later. If you look at, for example, the classic gem example, we have a lot of input parameters, but the interesting ones are our matrices, A, B, and C. C is usually the one which gets overwritten. Doesn't really matter which blast routine you look at. So if you don't have any alias info in that case, you have to assume that every time you overwrite C, you also overwrite A and B. Because what happens if you pass in 3 times the same pointer? And now you're not caching C only, but you're caching every single variable out there, which is indirect. So a pointer, a reference, whatever. And that's pretty bad. So that's why no alias is, not surprisingly, having a 10x performance difference here. And C++ is a little bit luckier, as we've seen on the previous slide. It only gets a 4x performance penalty, and that's because we do not, inside of our differentiated code, we do allocate a couple of functions, and the way C++ and C allocate memory is a bit more straightforward. For us, we have some more indirections, which makes it harder for our AD tool to understand that. We've been working on some fixes, but for other fixes, we want to have, for example, alias information on struct returns. Because right now, you can add no alias information to single pointers. You cannot really add no alias if you return a struct. So there's some work going on the LLVM side, which should make the unsafe Rust a bit faster. But generally, if you just stick to idiomatic safe Rust, you in this case should be fine. And well, it's not only about the runtime, it's obviously also compile times. If your code compiles for hours or days, few people will use your tool. So there are some challenges to AD. And the biggest one we have is we need really good type information, which isn't always there. So we need to figure out things. In the case of AD, simply a mem copy is not a mem copy. So it does matter if you copy 64 bytes of floats or 64 bytes of doubles. And if you do not know which one you do, as you can see on the bottom left, you might get the wrong derivative, which is pretty bad. So on the C++ side, we are lucky. C++ has TBAA, which gives you some information. Not all the way, but I mean, it's decent enough. On the Rust side, it's a bit bad. We don't have TBAA yet, and we will probably not get it. So we need to think of some other things. What I've been doing in my work over the last couple of years is finding out that LLVM has opaque pointers, and even before, you were not really supposed to use opaque types. So I thought I'd help it out. We have our own Rust IR, which is called MIR, and there we have types. So I started adding some analysis paths, and I've been lowering those type informations just to find out afterwards that we are now introducing opaque types. So there's some trickies to it. Good thing is we don't need type information everywhere. we'll be able to get a lot of that from just a few locations where it's relevant and propagate it inside of our autodiff tool. So we should be hopefully fine. And yeah, for compile times, we have some comparison from some chemistry applications, since I work a lot with chemistry people. They've been running some JAX code, which effectively out of memory during jitting time. Without jitting, the performance was unusable. With jitting, it was crashing during JIT time, so they were between a rock and a hard place. Rust came in, and we had 2 orders of magnitudes of compile time improvements. It's pretty simple code, so yeah, there's not much to simplify about the code. They just moved over. Rust has pretty nice interop with other languages, so now we are all happy without 2 magnitudes of improvements. We were wondering, can C++ do better? We have TBAA. How does it compare to the type information I create? And we compare Rust vectors to C++ vectors, or pretty much apples to apples, hopefully. Yeah, unfortunately, C++ was somewhere in between Rust and Python. Not as bad as Python, but still quite behind. We can see the baseline is, in all cases, kind of okayish, a couple of seconds for 50,000 lines of code. Not 50,000 in this case, but like for some lines of code. For the Rust, we made the interesting distinction. If you write unsafe code, you need to use specific functions. So it's not only slower, as we've seen before on runtime, it's also slower to compile, because now you don't use the standard built-in array brackets. You use some special function calls, which just takes longer to compile. The only special case here is release builds of Rust. Rust is really aggressive on vectorizing code. So the LLVM which I got from Rust was highly vectorized, even though the code was pretty random, which was interesting, whereas C++ code was just doing in the, scalar operations. So that explains a little bit why the Rust release build is so slow here. We obviously care about correctness a lot. It's an experimental feature, so I'm not going to complain we have perfect correctness and safety right now, but it's something we keep in mind. So to give some examples of why AD in Rust is tricky, especially if you go ahead and start modifying lower level IR, is checking shadow memory. So the way Enzyme works, or generally our AD tool works in Rust, is if you have a variable and you want to figure out how does this input variable correlate with the output changes, is you give it a shadow memory. Enzyme is going to write the shadow memory, use the shadow memory to write the gradients into it. So after a function call, a magic one, you can just read out the gradients from there. Now, Rust has a good type system, so whatever can be checked at compile time is going to be checked at compile time by our type system. There are a few types which have runtime properties. The first one is a vector, which is a dynamically sized array, so you decide at runtime how long it is. In the past, if you would call that function, df in that case is a function generated by autodiff, it would just do random things. Usually it's array out of bounds, so if you're lucky, it just crashes. If you're unlucky, it overwrites some memory next to it. We have extra handling for this case yet. There are a few other array vector types which we don't handle yet, but that's pretty straightforward. We just add some bounds checking and should usually be fine, since people tend to differentiate larger sections of code, because otherwise they could do it by hand. So a single bounds check once at the beginning of a function call isn't really relevant. I haven't even disabled it for my benchmarking, because there are some more cases where we do need to care about Rust types not being lowered into LLVM types. One is the mutability. So at lower levels, Enzyme is not really aware of which memory is mutable and what's immutable. We are thinking about having some improvements there for some performance optimizations, but for now, you can just bypass those checks if you pass the right types in. So Rust has mutable and immutable references. If you now create a struct with some immutable references inside, you might be unlucky. In some cases, we can recognize that data is marked as immutable. That's in the bottom line. In that case, we will warn you about it. But in other cases, like struct, it's too complex. Our analysis doesn't figure it out yet. So we need to improve that a little to make sure that no one is overwriting immutable memory on LLVM level. And yes, one of the last cases we have is enums. Enums is another case where we at runtime decide which type you're actually getting. Rust has a couple of rules about how you can cast one type to another. So generally, if the target type is going to be valid no matter what you write into it, then it's fine to cast. So if you have a float and you write that into an integer, like the finish resize, then you're probably going to be fine. If you have a pointer and now, especially like a 64-bit pointer, and start writing a float into that, it's probably not fine. And then there are even worse things, because the previous one we could eventually check on LLVM level. The last one is pretty bad because we cannot figure out on LLVM level we have niche layout optimizations. So reference does still have 64 bits. It has the same layout on LLVM level. We do not know what it means. So yeah. Do people have any questions? First of all, thanks for listening.
Thanks, Manuel.
I was very excited to come to this talk and learn about auto-differentiation. And I did see the slide go by with the exploration of auto-differentiation based on continuous function differentiation, specifically of the exponential function. And for me, that really doesn't bring it down to earth as to what the differentiation is that you're doing. We're not in a continuous domain. So maybe it's point-wise differentiation we're talking about. It's also not clear to me what the domain is that we're doing differentiation over.
Okay. So for that to say, usually autodiff tools are not super well defined on points which are not fully differentiable, with the reason that, for example, for neural networks, if you have like a ReLU, which at a specific point is not clear or has subgradients only, then that point will in reality rarely be hit. So autodiff tools tend to differ on what they return in that result. Enzyme specifically has the promise that you get a valid subgradient. For other autodiff tools, I'm not sure what they return in these cases. So it is handled and we do have some flags in which you can slightly alter the behavior for these specific cases. Yeah.
So can I surmise from what you're saying that the tool sort of lifts these integral functions into a continuous domain and then does symbolic differentiation on a continuous domain?
It's not necessarily symbolic. So the way it works is, since we are working on LLVM IR level, what we trace is the control flow. So since we have memory as the original inputs and we have shadow memory, which is moved along. So the way I usually explain myself AD in this level is, whenever we have some control flow, which might be not continuous, if we take the one branch for the primary one, we'll also move our shadow memory along the same branch. And that way we handle non-continuous cases.
Okay, so if I surmise that auto-differentiation is over a domain that's like the LLVM IR, is the input representation of the function that you're talking about, and then the differentiation that you're doing is really just like a very complicated algorithm that's hard to explain, but it's not really analogous to continuous differentiation any more than that.
You want to say something to that?
Yeah, absolutely.
Yeah, I just wanted to answer to the question, essentially. So the point is, you have the function that is defined by the program. And all the points of discontinuity that you might have are quite well defined. For example, it's the control flow, meaning that we can essentially, and the number of these points of discontinuity is actually countable. So you cannot have non-countable set of points of discontinuity for the function defined by the program. So in the way how autodiff is working is essentially when you have you have essentially the partially continuous function with the discontinuity points in the control flow. If you have if X, then A, else B, right? So you can think about this as the partially continuous function. So in the way how the autodiff is essentially structured is, well, you are differentiating the piecewise and then stick them together. So as a result, we usually have the subgradient, right? But it's quite well defined. So it's not like we extend into some continuous domain, no. So we're just doing things piecewise, and the reason why it is working and why it is providing well-defined results is because the program, the function defined by the program, can have only either the fixed or at least countable set of the discontinuity points.
Thank you.
Thank you, Manuel. Our next talk will start in 5 minutes.